In this lecture, I'm going to be talking about another approach for name entity recognition, and here we use the idea of similarity between different spans. So I'm going to be explaining this paper in 2020. So the idea is that interpretable rationales for models prediction play a critical role in practical applications. In this study, they developed models possessing interpretable inference process for structured prediction, and they present a method for instance-based learning that learns similarities between spans. So at inference time, each span is assigned a class label based on its similar spans in the training set, where it is easy to understand how much each training instance contributes to the predictions. Through empirical analysis on NER, they demonstrate that their method enables to build models that have high interpretability without sacrificing performance. So they consider it as a span classification problem, like previous methods, previous lectures, but here so is for each span, given each span, we want to know the probability of each class, and this score is just the dot product between these two vectors. And we go through all the spans for a given sentence. We go through all of that, and it's not just one sentence. For all pairs in your data set, you do it. So until now, everything is classic. So here they created some idea. So this is with the analogy of prototype learning. You may feel that all of them are very similar to prototype learning, but it adds slight modification or differences. So within a neighborhood component analysis, they define a neighborhood span probability, that each span will select another span as its neighbor from candidate spans in the training set. And they exclude the input sentence and its ground truths from the training set. So they compute the probability that a span S sub I will be assigned a label Y sub I. Because, for example, given a span, the spans that are neighbors to that could be S1, S2, S4, so all of these, or Sj. So all of these are possible things. So we should add all of these events in the context of probability theory, or possibilities. We should add all of these to get the probability of label. Because what it means is that if something is a span of another span, then it means that they have the same, according to definition, they have the same label. So we should consider them as well. So that's why we are minimizing this negative likelihood that we have calculated in the previous slide, this slide. So we are calculating it here, and then we do it for all data sets, and for each sentence we go through all the spans. And at inference we predict yi hat with maximal marginal probability. So it's again this form, but we want to see which y is the maximizes this probability. The neighbor span probability depends on the entire data set, so it is not practical, it is intractable. But they use a trick here. They use random sampling. They just need case sentences. You don't need to go through all data sets. You just need case sentences. So it's a kind of random sampling process. And so they randomly sample case sentences for the mini batch at each epoch. So with a single GPU, it's less than 1 day to train the model. And the data that they use is again like flat NER. They use Connell 2003 and nested NER on GNI dataset. And the baseline is the classifier-based span model, but the difference between the instance-based and classifier is whether to use softmax classifier or not. The rest of them is classic, use span representation and scoring. Even the score between two spans is just a dot product between their representations. And when you compare it for example, the classified burst, which is our base model, with this proposed in this lecture, you will see that slight modification, better improvement, and the F1 score is around 90%. Of course, flat NER is simple, but for nested NER, it has 74%. In comparison to just the base, which is 73, so 1% improvement. And again, for BERT is the same, almost the same thing. For nested NER, which is more difficult than flat NER, they use 73%. And you see F1 score between different methods, the classifier based or instance based. They're almost the same. And this is the visualization for entity spans, location, organization, person, miscellaneous. So you see different clusters. So even the shape is very similar. Here we have some separation, but in the classifier base it's more uniform. So we have a query, we have some support, and we want to know which one matches which one is closer to which category.